students. Good morning, students. Previously, we discussed valency bond theory, continuation of valency bond theory here. According to valency bond theory, complexes are two types: inner orbital complexes and outer orbital complexes. We discussed already in the previous video what is inner orbital complex, what is outer orbital complex. Inner d orbital he is using in hybridization, that is inner orbital complex. Ligands here 6, ligand here 6, here this is bidentate ligand, here also 6, coordination number is 6. All these three are octahedral complexes. Octahedral complexes, inner orbital complexes, hybridization is D2sp3. So inner d orbital is used in hybridization. Here also coordination number is 6, octahedral complexes. Outer orbital complexes means outer d orbital is using in hybridization, overlapping, sp3 d2 hybridization. Observe each complex magnetic behavior of each complex. So manganese here, oxidation state of the manganese in this complex, MnCN6 minus 3. Cn minus, you know that already, negative ligand. Here 6 ligands are present. For getting minus 3, manganese is how much? Plus 3. So manganese valency 3d5, 4s2. Manganese plus 2. After losing the 3 electrons, from here 2, from here 1, 3d4, 4s0. In the d4, how many electrons are available? 4 electrons are available. The 4 electrons from the d4, 1, 2, 3, 4. Beside the 3d, here the 4s is present. Beside the 4s, 4p is present. This is 3d, this is 4s, this is 4p. Now what is happening here? What is inner orbital complex? Inner d orbital is using in overlapping. That means with ligand coordinate covalent bond is formed. So to that, one of the electron is moving from here to here. Electron is moving from here to here. After moving that electron, 1, 2, here the electrons are existing like this. So now what is the one more electron is moving from here to here. One more electron. Now vacant orbitals are available. That vacant orbitals are available. These two vacant orbitals involved in the overlapping. Here d orbital, here the 4s orbital, here 4p orbital. How many orbitals are available? 6 vacant orbitals overlapping with 6 Cn minus ligands. Coordinate covalent bond formation takes place. 6 is, so inner d orbital is using in the hybridization, D2sp3 hybridization. So magnetic behavior is diamagnetic because of electrons are pairing takes place. So beside the 4s, 4p, what is present in the fourth shell? 4d is present. In hybridization, 4d orbital is utilizing, that is outer orbital complex. Inner orbital complexes basically observed in strong field ligands. Strong field ligands. Cn minus is a strong ligand. And oxalate ion in some cases act as a strong ligand, in some cases act as a weak ligand. So cobalt plus 3 case oxalate ion, cobalt plus 3 case oxalate ion act as a strong ligand. So it is the inner orbital complex. Hybridization is D2sp3, diamagnetic in nature, Mn plus 4. This is the example. Next example observed here. One more example. Next example. Next third example observed here. Third example, cobalt C2O4 is the oxalate, is a bidentate ligand. Here the minus 3 charge is present. Oxalate charge is minus 2. Here the 3 ligands are present, minus 6. For getting minus 3, cobalt charge how much? Plus 3. So cobalt valency is 3d6, 4s2. Sorry, 3d7, 4s2. So cobalt plus 3. So 3d6, 4s0. In the D, how many electrons are available? 6 electrons are available. 1, 2, 3, 4, 5, 6. 6 electrons. Here the 4s is present, here the 4p is present. 4p. What is happening here? So electrons pairing or non-pairing is given based on the magnetic properties values. Valency bond theory main drawback is doesn't explain the ligand nature. Valency bond theory. It is given this data, hybridization data is given based on the magnetic behavior. Don't forget that point. Here the electrons are pairing takes place, moving from here to here. Now after shifting that electrons, 1, 2, 3, 4, 5, 6. So 2 vacant orbitals are available. Here 4s, this is 4p. Which orbitals are using in hybridization? Oxalate ion overlapping with these 6 vacant orbitals. Hybridization is D2sp3. Any unpaired electrons are there? No unpaired electrons. So magnetic behavior is diamagnetic. So it is a inner orbital complex, low spin complex. Inner orbital complexes also called as low spin complexes. Low spin complexes. Another name is there. That another name is spin paired complexes. What happens here? Spin paired. Here paired. Here paired. Spin paired complexes, low spin complexes, inner orbital complexes. The meaning is same. So inner orbital complexes basically possible in the strong field ligand cases. Strong field ligand cases. Strong field or weak field are given based on the magnetic properties. But it is not properly explained by valency bond theory. That explanation is given in the crystal field theory. Next, outer orbital complexes observed here. Outer orbital complexes. Now here observed here, which ligands are present here? Ligands, Cl ligand, fluorine ligand and fluorine ligand. Basically halogens are weak ligands. Remember this. Among the halogens, which is a more electronegative element? F minus, Cl minus, Br minus, I minus. Among the halogens, comparison point of view, F minus is a strong ligand, I minus is the weak ligand. But basically halogens are weak ligands. Comparison point of view, fluoride is compared to iodine is a strong ligand. Compared to chlorine, fluorine is a strong ligand. So observe that hybridization of these complexes, outer d orbital using electrons are not pairing takes place in these cases. Just one example. Look at here, Mn Cl6 minus 3. Example, look at this complex here, Mn Cl6 minus 3. What is the manganese oxidation state here? Cl is minus 6, manganese is the plus 3. Manganese plus 3 means 3d4, 4s 0. 3d4, 4s 0. In the D, how many electrons are available? 4 electrons are available in the D. 4 electrons I am writing here. 1, 2, 3, 4. Here 4s is present. Here 4p is present. 4s, 4p. 4s, 4p. So octahedral complex requires 6 vacant orbitals for bonding with ligand. But how many vacant orbitals are available? Here 1, 2, 3, 4. Beside the 4p, what is present? 4d is present. Beside the 4d is present. This orbital is involved in the hybridization. So here Cl donate the pair of electron. Cl donate the pair of electrons. Cl donate the pair of electrons. 6 Cls are present. 6 Cl minus ions donate the pair of electrons to vacant orbital. So what is the hybridization? sp3d2. Here one vacant orbital is present in the 3d. 3d means this is n minus 1d. This is nd. Here the 4, here the 3. It is not involved in the hybridization. Why it is not involved? How it is possible? That is not explained in the valency bond theory. That is explained in the crystal field theory, splitting case, T2G and EZ cases areas. So how many unpaired electrons are available? 4 unpaired electrons are available. 4 unpaired electrons. Outer d orbital is used. So outer orbital complex. Outer orbital complex also called as high spin complexes. High spin complexes. Another name also is there. Another name is spin-free complexes. Spin-free complexes, high spin complexes, spin-free complexes, and outer orbital complexes. So weak field ligand basically forms outer orbital complex. Strong field ligand basically forms low spin complexes. What are the drawbacks are there in the valency bond theory? Valency bond theory does not explain proper explanation of the magnetic properties of the complexes and the stability of the complexes, color property of the complexes, thermodynamic kinetic stability of the complexes. Two more examples, valency bond theory, I will explain another video.